So now let's take a look at one functional device. And it's really using the fact that we can earn free lunch or free ticket. So now we have a magnetic material. It's shaped into a ring. Okay. On this ring, we have a lot of wires winding around it. Okay. In this case, we winded n number of turns onto this so-called magnetic core. Okay. But somehow, we cut the magnetic material here, so we have a small gap. So inside this gap, we only have air. Okay? So this magnetic core is having a small air gap, and then on this winded wires, we conduct a steady state current of I0. So the example is asking you to derive the resulting magnetic field intensities inside the core and inside the gap. But before we go into the mathematical details, just like the student who asked me the question, it's more important that we know what we're looking for. We need to have some kind of physical picture to have a valid anticipation before you move into the mathematical derivations, right? So the first question is, what is the functionality of this device? Why do we bother to make it, and why do we bother to cut that small air gap? By cutting that small gap, you are, well, in some sense, you're destroying your magnetic material, right? Initially, it's a beautiful ring, so you can wear it. But now, with a gap, I mean, it's worthless. So what is the functionality of this device? Try to combine all the messages I gave you in the previous class. It's still on the blackboard, right? You have all these definitions, the physical pictures, the number of field lines. So the key word is the number of field lines. What is the benefit of having a magnetic material? This magnetic core is having an absolute permeability of mu. Meaning, this mu is not equal to mu 0, but something else. So by default, this is telling you this magnetic material can generate induced magnetic dipoles. And when you have the induced magnetic dipoles, you must think hard. The functionality of the induced magnetic dipoles is to potentially give you more and more effective field lines, right? So you have a huge B value. Okay, so that explains why we are winding all these wires around the core, because we're hoping, oh, I shouldn't be answering because I'm used to having no students in the classroom. Anyone having some feedback or thoughts? You're free to raise your hand and share your opinion with us. Yes. Yeah, right, exactly. So that I'm trying to translate his answer into English and maybe adding some my personal opinion. So the student is saying In this case, we can increase or enhance the magnitude of the field. Okay? So I'm following up on that. I can increase the number of magnetic field lines. Okay? But up to now, all these two answers, increasing the number of field lines is only true, it's even true without this air gap. With or without this air gap, right? Inside the core, we have a mu value, meaning that we can produce more field lines. So why do we cut the gap? The key issue, you are going to be future engineers, right? So why do we cut the gap? In essence, we destroy this ring, this core, for some good reasons. So why do we need to cut the gap? Or let me ask you the question in another way. Okay, it is true that inside the core, we can enjoy the benefit of having a lot of magnetic field lines. But so what? How can you really access or enjoy those field lines? You go to the museum, right? You see this super pricey pictures, antiques. They're very expensive, but you don't own them, right? So if you don't cut the gap, it's a very beautiful core, having lots and lots of magnetic field lines inside. You can look, but you cannot eat. So as an engineer, if you want to enjoy the benefits of having lots and lots of field lines, you need to cut the gap. Once you cut the gap, you might be able to put something inside the gap, right? Otherwise, everything is self-contained in the core. How can you use it? So we cut the gap in the hope that inside this gap, there are beautiful relations, right? There are beautiful, magical things that we can use. So we can put something inside the gap and achieve some applications. Okay? So basically, the functionality is really inside this gap. So we're going to focus the gap. Now that we know the functionality, and somehow I already give you the hint, inside the gap, we have huge magnetic field intensity. Okay? So that's my anticipation. Even though I only apply very weak current, I can generate huge field intensity. So the H inside the gap can be made very high, even though I apply very low current. That's my definition of free lunch, right? Okay. So let's take a look. How do we solve this mathematically due to our understanding? Well, the first mathematical equation is always the most difficult. So how do we start? So take a good look at the picture. All these red dashed lines are used to denote the field lines. As we mentioned, magnetic field lines form self-closed loops. Okay? But then you see this, the so-called leakage flux. What are they? So this is the moment of truth. Okay. What are these leakage flux? Here you have two, right? You have two. This means inside this device, even though you generate a lot of magnetic field lines, but some field lines are lost somewhere, so they are no longer guided by the magnetic core. Think of water, okay? Think of water as magnetic field lines. So you have a tube. Ideally, all the water will be guided by the tube, but then somehow on the wall of the tube, you have a small hole. So you have water leaking out, which is undesirable. You don't want water to leak out, okay? So for this moment, we're going to assume we have no leakage flux. Once you have one magnetic field line, it is well guided and propagates in the core. Okay? We forget about the leakage flux. If time permits, I will talk about it later. I'm going to show you the first mathematical equation. You are free to challenge me. Okay? I love challenges. So the first equation is this. This is saying, hey, the magnetic flux density inside the core is equal to the flux density inside the gap. Again, this is the real moment of truth. Do you agree to this fact or pseudo-fact? Do you think it's valid or not? Again, when we talk about B, we are talking about the maximum amount of field lines, right? So this is telling you my assumption is all the magnetic field lines generated inside the core due to the free current and due to the induced magnetization current are all guided by the core. No leakage. But the problem comes when all these field lines propagate somehow and reaches to the gap. What is going to happen? Under this equation, I'm saying that all the field lines, for example, I have 100 field lines inside the core. When it sees the gap interface, all 100 field lines come out and go into the gap, and all 100 field lines re-enter the core without losing a single field line. So this is the assumption of having no leakage flux. Okay? This is a very strong assumption. So the number of field lines inside the gap is equal to the number of field lines in the core because there is no loss. There's no leakage. Okay? Very simple mathematical equation, but already covers some strong assumptions. And as an engineer, you should be asking how to achieve that. If this is the target from your boss, your future boss, if you cannot meet it, you'll be fired. How are you going to achieve the design to ensure this is true? So let's talk about it. Any thoughts? Any particular geometry that you have to pay attention to? In this case, the nominal radius of my magnetic core is R0, right? The gap length is Lg, the length of the gap. If I am a bad student in this class, after graduation, I found my first job. My first job is to achieve this. So I removed half of the ring as my gap. And I show my boss, hey, this is my professor. He taught me this, right? So I cut the gap. The number of field lines remain the same. I'll just be fired in 3 days. Why? Because if you lose half of the core material, you're not really having the core, right? So as a future engineer or professor, researcher, tell yourselves, what is the basic requirement on this Lg? You have to make it as small as possible, right? So how small is good? It depends on your future usage. What is the thickness of the material you are going to insert into the gap, right? If your future material to be inserted is 1 millimeters, just cut it 1.1 millimeters. If it's 5 millimeters, just make it 5.1 millimeters, right? Big enough to use, and that's it, all right? So now we're talking about a very practical device, so we considered the practical issues. Now, if this is true, right, we cut a very small gap by ensuring that Lg is very small as compared to 2 pi r0. What is 2 pi r0? The total length inside the core. Remember, why is this length important? Because Ampere's circuital law is now having closed loop integration of H. So we do care about the length, right? In this case, as we walk along the core and enters the gap and re-enters the core, we want to form a closed loop. So that is represented by contour C. Okay? Ampere's circuital law tells you within this closed loop how much current, free current, do you encompass. So in this case, each winding gives you 1 I0. So total, we know we have N turns, so the number of current encompassed is N times I0. Okay? So now let's try to do this closed loop integration. We have two parts. H is B divided by mu, right? So H core, this is H core times its corresponding length, 2 pi r0 minus Lg, right? This is the effective length inside the core plus the gap H. This is H gap, but because the gap is equal to core, I'm using the same perimeter, right? And times Lg is equal to that. So immediately you have the final result. So the final result of the flux density inside the core and inside the gap, they're identical. They are in the direction of phi direction. How do you know it's in phi direction? Current is going in, right? From the bottom to the top. So you use your 4 fingers. Basically, this is the flow direction of your current, and therefore your thumb is pointing in the direction of your B. So basically, your B is in the phi direction. Okay? Phi direction, and this is the magnitude. Well, the interesting thing is, if you still remember, what I'm trying to prove is this device is very useful so that I can send in very weak current, but I can generate huge, very strong field intensity inside the gap. So what do I have to do to prove my point? I want to calculate H. I want to calculate the field intensity inside the gap. How do I do that? I simply divide it by mu 0. Right? Gap is vacuum, assuming there's nothing inside. Right? I take this B core value and divide it by mu 0. That's my field intensity inside the gap. Now, if I want to know the field intensity inside the core, I'd simply divide it by mu. Okay? So looking at those two H values side by side, or top and bottom, please try to come up with a conclusion of your own so that you can remember forever. If you compare the amplitudes or the magnitudes of these two, which is stronger? Which H is bigger? Well, mu is, or relative mu r is greater than 1, right? So definitely this is larger. So this divided by a larger quantity, this is weaker, right? So if you are a good engineer, you know that under the assumption of no magnetic flux leakage, the number of field lines in the gap is equal to the number of field lines in the core by making sure that the gap length is very, very small. You can indeed generate stronger field intensity in the gap as compared to the core, right? So these two, direct comparison, this is stronger than this one. But how much stronger? Coming back from the engineering aspect, how can you make this ratio, Hg to H core, extremely pronounced? You want to find a core material which is having huge mu value, right? So this is what I call the free lunch. So actually, I mean, can you sense it's really not free lunch because we worked so hard. So nothing is really free. We accumulated and we integrated all this knowledge into this simple device. So it's really not free lunch. We should be paid a lot, right? So you buy this one, you wind the wire, costs 100 NT, you sell it for 2,000 NT. Nothing's for free. Okay, that's what companies and engineers do. And professors always provide free knowledge. Yeah? Okay. So, if you want to enjoy the benefit of using the gap region, having very strong field intensity, but by only supplying very low current, you have to choose a core material which is giving you high mu value, and you want to run a lot of winding numbers, right? By increasing n, you also increase H, right? So that's a real free lunch part. You use a longer wire, you increase the number of winding, you increase n, you can even further reduce the amount of current required. Okay? Question up to now. I'm trying to show you that problems, please do not view the example problems as only problems. I'm not here to train your mathematical skills. I'm here to provide you or consolidate your physical insights. You have to have a clear physical picture. You have your anticipation. You understand the problem, and then you do your mathematical derivations. Okay? I hope that is also reflected in the examination problems, hopefully.